Hi, welcome to this Druid Summit 2022 session on Druid 24.0 and its new nested JSON support. My name is Sergio Farragut. I'm a Senior Developer Advocate here at Imply. And today, agenda is we're going to talk first about the motivation for doing this feature. We'll talk about what the options are for ingesting JSON and querying JSON. We'll look a little bit under the hood and see how the nested JSON is actually being indexed. And finally, we'll talk about the performance characterization. We did a few benchmarks on this feature, and we'll show you those results. So, what is nested JSON and why support it, right? So nested JSON is this idea that a JSON structure can have multiple levels of nesting. That means it can contain nested JSON objects within fields of the higher level JSON structure. So this allows us to be very expressive with details about things such as an order line item, where you have the payment may be different and may have different attributes. So the portion of the order is a different structure than the portion of the item that's being sold, as an example. The product within item has different fields inside it to describe it. Anyway, it provides a very expressive form of data that tells us about relationships between the data, so it's a common form of data. With Apache Druid, before this release, this kind of structure could be flattened, but that requires some work, so let's talk about what that work is. This work is about mapping the individual nested fields into columns within the target table, so that each nested field ends up in a single column in the Druid table. This requires us to provide static mapping rules that usually specify in a flattening spec. So this is specifying the target column and what source field it comes from. So it's things like order underscore date comes from the order field, the date subfield, or payment authorization ID comes from the order field, the payment field inside that, and the authorization ID field inside the payment. So you need to create all these rules for all possible fields within the JSON. Now, this has a few issues, right? First of all, you have schemas that change from record to record, as an example, right? So in this example, we have two records of product, and we'll see that the attributes associated to each product are actually very different attributes, which makes sense. Bicycle doesn't have a refresh rate or a dynamic contrast, and a flat screen TV doesn't have a bike type or how many speeds it has. So we'll see this kinds of structures in the real world. So in order to deal with this, you'd have to create all the possible mappings to cover all the different structures for attributes in this case, right? Attributes bike type, speed, attributes for refresh rate, and dynamic contrast. And if you have thousands of products, this could get fairly complicated. Additionally, schemas change over time, right? So if fields are added to describe, in this case, products in a better way. So with these things, we'd have to additionally, whenever the data changes or wherever the schema changes, we'd have to update these rules, right? We would have to continuously update the mapping rules for any of the new features, and we'd have to know that there are new fields within the JSON structure in order to do this. So that sort of drives the motivation for doing this automatically, right? Because, why? Because who wants to do all that, right? Who wants to keep up with the changing schemas and having to change the flattening rules? So that's why we want to do it automatically. So with Druid 24, nested JSON is ingested directly. It can be done through SQL-based ingestion or through either native streaming or native batch ingestion. All of the literal values within the JSON structure are automatically indexed. That means they each get the dictionary encoding, they each get indexed, and they each get compressed, which results in fast filtering, fast aggregation on any of the JSON fields without having to do any mapping ahead of time. So even if schema changes across records or across time, this kind of ingestion will automatically deal with it. So let's talk about that ingestion, right? How do we ingest the JSON? It's actually also quite simple. So given the JSON record on the left, where we have two nested JSON objects in the ship2 and the details fields, an ingestion SQL could be as simple as the one we have on the right. We're using a replace statement where we're selecting that ship2 and details fields as part of the structure that we're going to be creating the shipping orders table with, right? And the only thing you need is in the from clause where we're specifying the external data source, the schema needs to contain those fields, and they need to be identified as complex JSON type. That's really all that's needed. Once you do this, you run this SQL to do the ingestion, and it will automatically do all the indexing of the JSON fields within the ship2 and the details sub-objects. Within native streaming and batch ingestion, it's just as easy. All you need to do is in the dimensions spec, specify the dimensions as you usually would, and in the case of the JSON fields, just specifying them as type JSON. The rest of it is automatic. Now, there may still be situations where you want to extract fields out of the JSON that you're ingesting. And you can do that either through SQL ingestion or through native streaming or batch ingestion by using one of these kinds of functions, right? First of all, we have JSON value function. This will extract an individual field as a literal value from the JSON object. And so you can extract that and create a single column out of it. You can also use JSON query, which will extract a portion of the JSON structure as a JSON object itself. So address is an example of that, right? Address is a JSON object itself. So you may want to extract that and store that as a single JSON object and still ingest it as JSON. So that's what JSON query would be for. And finally, JSON object, which allows you to build objects from multiple either literal fields or other elements of other JSON objects within the input source. So that it's really that easy. Ingesting JSON is really just about identifying it as such, as a JSON field, and either through SQL or through native ingestion, you can ingest that data and have that automatic behavior. Now let's talk about querying JSON. So first of all, because these JSON fields that we've ingested are dynamic in nature, we don't necessarily know all of the internal fields in them, right? You may be ingesting a set of files and the structure of those JSON objects changes over time. So in order to inspect the JSON and figure out what fields are available, you can use the JSON paths function. To get a single list of all of the possible JSON paths across all of the rows, you can do something like this, where you're using an array concat ag function to create a single aggregation of all of the different JSON paths available within a particular JSON column. And the result would look something like this. You can use, at query time, JSON value to extract any of the fields, whether they are dimensions or metrics. JSON value will extract them. It's actually not parsing the JSON at this time, right? This time it's already been ingested, and using the JSON value function is just a way of telling the engine which column to access, which of the automatic columns that it generated to access. So it still has all the advantages of accessing the columns as if they were flattened, but this is how you access them with the JSON value function. You can use JSON value both for dimensions, so you can extract, in this example, we're extracting country out of the ship2 JSON field as a grouping field for this query. And you can extract columns in order to calculate metrics such as the price and the total revenue that we're calculating here by extracting price from the details JSON column and doing a sum on it. Additionally, you can use them for filtering, and this is where all the indexing capabilities that are automatic come into play, because by using this condition where JSON value on the ship to field for country in or equal or greater than any of the condition capabilities that the Druid can do, you'll be able to use the underlying index to find these rows and do so very quickly. So you get the same speed that you would from a regular JSON column, but you access it through this JSON value function. I'm sorry, through a Druid column, not a JSON column. So let's take a look at what it's doing under the hood, right? So what is it doing with the JSON? How's it translating it to columns? So first of all, it takes a look at the JSON structure and parses it and finds all the literal fields. So those are the ones we've marked in red here, all the leaves of the structure. So each of those is converted into a column, a Druid column structure, where the dictionary is created for each of them. Each of them are indexed, and the data is stored in encoded form and compressed, as it would be in any other Druid column. It's just doing this automatically. It will treat arrays in a particular way, right? So each entry in an array will generate a group of columns, as it's doing here. So we have two entries in the phone numbers array. So we'll see one column for phone number 0 number and one column for phone number 0 type. So each of the internal fields within that array will get its own column, and we'll get a separate set of columns for phone numbers index 1, right, where it'll also have phone numbers 1.number and phone numbers 1.type. So this is how it translates arrays at the moment. This means that when you query them, you will also need to specify the array index to query them, which is not ideal in some query situations. And this is why there's future work in this area that we'll talk about at the end of the presentation. And finally, it recognizes the data type of those JSON structures, so it'll create either long, double, or string columns when creating the automatic indexing. So let's talk a little bit about performance. There's barely any change at the query time in the comparison here, right? What we're seeing is in this chart is we've ingested the same set of data in two different forms. One is in flat form, so each of the columns is an individual column. And in the second case, we've embedded them all into a JSON structure and queried them as nested JSON columns. So the comparison here is between the flattened version of the column and the nested version of the column, and different query patterns and how they're affected. So we can see here that a lot of the query patterns are, the performance difference is barely noticeable. There's minimal variation in most of the cases. There's some cases where the nested JSON actually behaves faster. Now, there's a reason for this. With nested JSON, there's an improvement to support indexing of numeric fields. So that means that if you're doing equality conditions or in conditions on numeric fields, it will perform better than the flattened version, because the regular Druid columns don't yet support numeric indexes. So that's why we see this improvement. Now, that support for numeric columns in traditional Druid columns, non-nested ones, is coming in the near future to Druid in general, so that this distinction won't exist in the future. Now, we do see a couple of cases where the performance is actually much slower when using nested JSON. And that's specifically when we're doing range conditions on numeric columns. I was talking to one of the developers, and he mentioned that this is because there's still an implementation missing for an implementation of the optimization for ranged evaluation of these kinds of columns for numeric columns, and that's why we don't see that that improvement here. But that's also something that's in the works, so this should be resolved in a future release. So from a storage and ingestion performance impact, we see that from a storage perspective, there's growth, right? There's a larger storage footprint for nested JSON than there is for the flattened versions. This is because nested JSON has stores more different structures, right? It stores a global dictionary. This is a dictionary for the whole JSON column that includes all of the string long and double values across all possible fields within the JSON. And then there's local dictionaries for each of the individual fields. Also, the raw data, the raw JSON, is stored. It's stored in a compressed form, but it's stored right now so that it can be accessed at query time. And the individual fields as columns, which would be the equivalent of the flattened ones. This produces, in one example, in the KTTM nested data, it produces about a 40% increase in size. This will likely vary a lot based on your data demographics, but there is an expected increase in size, and 40-50% is probably a good ballpark. From an ingestion performance perspective, it is significantly slower, and that's because it's doing a lot more work to automate this flattening capability. And just as an example, the KTTM nested data, the flattened version took 48 seconds to load on my laptop, and the same ingestion using the complex JSON, and so the automatic indexing behavior, took a little over 2 minutes. So it's approximately 2 times as much work as it would be to just do the flattened version. But I think the benefits are actually quite valuable here in having this dynamic behavior on any JSON structure and just being able to query it with Druid's performance. So a little bit on future work. There's ingestion performance is one of the items that we're looking at. And the storage footprint, looking at the possibilities of maybe removing the raw JSON or optimizing the structures in some form that reduce the additional storage footprint that this needs for now. Better array support. So we talked about the arrays and how you need to specify the indexes when querying them, querying individual array items. So we're looking to better support them by automatically unnesting, or providing the functions to unnest those arrays and treat them like arrays. Support for other nested formats is in the works as well. We're looking at Parquet, Avro, and ORC formats to support that also have nested structures, and adding some customized ingestion control. This is the idea of just including portions of a JSON based on a path and wildcards, or excluding certain paths from this automatic ingestion behavior, which should be useful to segregate the portions of a JSON that you want to work on. So just as a summary, we talked about the motivation. Flattening JSON is a bit of a burden if you're going to do it manually. So doing it automatically and having all of this be automatically indexed and having the performance as if you were flattening them is kind of great. Ingesting the JSON, you saw, is very simple. It's really just about identifying the JSON. And then querying the JSON requires a little extra syntax, surrounding things with the JSON value functions, mostly where needed, both for selecting, grouping, aggregating, and filtering data. But it comes with the great performance that Druid is known for without having to flatten, which I love. Under the hood, we talked about how all of the columns are automatically indexed, and how arrays are treated, which is something that's going to be improved. And we saw that the performance impact isn't really the only impact is if you have conditions that are range conditions on numeric columns. That's the only negative impact. The rest of it behaves incredibly well. So we hope you start using nested JSON soon. And I think it's one of the great new features in Druid 24.0. So with that, I'll open it up for questions. Thank you.